So, we looked at climate sensitivity and we looked at some model sensitivities are not always the same as what we see in nature, but when we saw that if we take a long period of time, multiple decades, then the trend produced by the models is very close to the observed trends, which means the forced component related to global warming or anthropogenic CO2 increase and so on are pretty reliable. So, we have been looking at how the representative concentration pathways or RCPs are defined, and we will look at a couple of more details of how future changes in energy production, energy use are guessed or assumed or estimated, and then get into actually what the model projections look like. So, this is starting with the projections of carbon. So, in 2014 or so, the estimate for 2017 was offered, and there was a slight flattening of the CO2 emissions from 2014 to 2016 or so, and you can see that there was also a dip in 2008. So, every time there is a financial crisis or some kind of a economic slowdown, there seems to be a flattening, but that always turns out to be temporary, because in fact 2017 did pick up on the emissions, and it is now the fourth warmest year on record, in the instrumental record. So, keeping those kinds of things in mind in the context of historical evolution of CO2, the projections are made into the future, and this is the same thing that we looked at before. I will show it again a couple of times, but you can see that there are fainter gray lines and green lines and so on, which are multiple scenarios of how net increase in CO2 emission affects global warming. So, this is just to show the range. So, if you in fact manage to reduce the emissions to negative with respect to the base period, then the warming will be somewhere in the range of 2 to 3 degrees, and if we are unable or decide not to do it, then the warming can be 5 to 6 degrees. The 2 degrees centigrade you might have already heard of, because the so called Stern report many years ago produced a climate impact assessment and impacts on GDPs, how much it would cost to deal with climate change and so on, and suggested that 2 degrees C warming with respect to the pre-industrial temperature would be the most beneficial or least harmful one. It didn't have incredibly solid scientific foundation at the time, but since then lots of work has been done to show how going above 1.5 or 2 degrees centigrade can put us into points of no return. The other terminology used is no analog state, which means if we look at all the past climate changes, we might see futures that doesn't look like anything we have seen in the past. That always is a problem, because if you really want to manage the unavoidable or avoid the unmanageable, then you have to know what is unmanageable. So, those are kind of discussions that get into lots of socioeconomics, politics, policy and so on. We will come to more of those. Putting that together now, this is showing the cumulative anthropogenic CO2 compared to 1870. So, if we keep on emitting according to the RCP scenarios, what are the cumulative CO2s that we will end up with? So, here is the observed CO2 in the 2000s. You have to remember this is showing gigatons of CO2 and gigatons of carbon. So, you have to adjust the mass of which gas you are considering. Nonetheless, these are the range of CO2 emissions that will produce the range of temperatures with respect to the, let us say, beginning of the industrial revolution. And these are the baselines of concentrations that we will end up with. Warmings that correspond to these baselines are the median values, and they are computed with a simpler model. There are all kinds of technical details which you don't have to worry about, but the main thing to note is that knowing the observations, there have been some uncertainties in the past, but in the future projections also you have a range of scenarios that you generate, which means the median warming also has a range. So we always typically give a range. This is less than 6 degrees, less than 5 degrees, and so on and so forth. So that's something to keep in mind. And here it is showing total human induced warming, which means not just CO2, which is shown here, for example, because once you start the energy use and so on, we know that it's going to change not just CO2, but it has also been changing methane, nitrous oxide, land use change, sulfates, and various other things like melting glaciers, reduced albedo, and so on. So the energy kept in the system is going to produce something that is a total contribution from human beings. The same figure here, same numbers as before, is showing. So here is gigaton carbon, so we are somewhere in this range. Again showing from 1890 to 2010, and then projections for the RCP 4.5, 2.5, and the biggest one 8.5. These are increasing at 1% per year. So as I said, if you increase 1% per year, it takes about 70 years to double. That simple compounding calculation you can make, but again you are accumulating along the way. So it's always important to remember that, because concentration is something you measure instantaneously. That's not a measure of accumulated carbon. That's just what's in the atmosphere in terms of the concentration. Okay, so added to that, these two are put together here now, and this shows the larger range that you end up with. So just the CO2 induced warming is here, and when you add other changes that happen because of human activities, the maximum range turns out to be over there. So these are the kind of projections that come out of all the models. So many models are involved in producing this kind of figure, and we will see how many scenarios are produced. You get some sense of that here. So these are ranges of scenarios. All these weaker looking lines, or not the thick lines, the thinner lines, are all the range of model simulations. Okay, the dimmer lines, whatever you want to call them. So just to look at some more on energy calculations that are included for future emissions. This is million tons of oil equivalent estimated demand of energy into the future going to 2050. Will obviously continue to increase. It is about 5 times the estimated energy use in 1965, and the net electricity generation by fuel in 2012 was somewhere here in terms of trillion kilowatt hours per year, and these are the various combinations. So renewables, coal, natural gas, nuclear, and petroleum. So coal use into the future is not expected to decline according to the estimates by the Energy Information Association. Coal is a complex matter, because coal, there is a lot of it. If you calculate how long coal can be burned at the rates we are burning now, it's somewhere in the range of 800 years or maybe longer. So the human question then, which we have to keep on coming when we think about future projections and future decisions and mitigation and adaptation, is that can anybody afford to leave the coal in the ground when the other fuels are more expensive, or you cannot afford them? In a country like India or China, can they afford to keep the coal and not burn it and rely on just renewables or importing oil and gas from elsewhere? So that is a very difficult question. So that's why these kind of estimates are important, and it shows in a different way here the energy consumption by fuel type. So going from 1990s, you can see again similar kinds of allocations: nuclear, renewable, natural gas, coal, and liquids. So you can see that coal continues to be a player into the 2030s and 40s, which is very important, because countries like India, which have committed to Paris Climate Agreement, have committed to reducing carbon emission. So now they have to start deciding their portfolio of energy. How will they reduce carbon? Will they ramp up the renewables so much that they can reduce coal use, or will they start investing in the so-called carbon capture and sequestration technologies? What happens if they are not available? What happens if they are invented by some other country and it becomes very expensive for you to buy? Or even things like refrigeration, HFCs, we saw that it is almost 2000 times more powerful than carbon dioxide and can stay in the atmosphere for a very long time, can stay in the atmosphere for several thousand years, will be phased out, or the agreement is that it should be phased out, but we don't know what it will be replaced with. Again, who will produce it? Can a country like India afford it? And as the air conditioning demand keeps going up, how is the energy use going to be affected? So, I will jump a little bit ahead to mitigation and adaptation strategies and show one figure. We will come back to it in much more detail later on, but in this context I want to just mention that if you decide on a range of CO2s going from 580 to 720 ppm, which is the higher end, 530 to 580, 480 to 530 and 430 to 480, which is very close to where we are now. We are at 403 to 405. We are increasing by about 3 ppm per year, and that 3 ppm per year itself is increasing. So, the increase in CO2 itself is accelerating. So, we will hit this very, very quickly. So, in that case, what are the low carbon energy share you have to adapt in the coming years? So, obviously, if allow for large CO2 emissions in 2050 or 2100, you have an option of a wide range of low carbon energy as a share of the primary energy source. But if you really want to aim for low total carbon in the atmosphere by 2050 and 2100, then the options become very narrow. You must include 80 to 100% of your portfolio as low carbon energy sources. What they are, obviously you have to still decide: biofuel, nuclear, renewables, solar, wind, etc., wave maybe, and so on. But nonetheless, it gives you a sense that once you have chosen your pathways, it begins to put a restriction, or it begins to define your choices of energy. And of course, it will also seep into how you produce your food, how you produce yours, how you do your transportation, and so on and so forth. So, just keep that in mind. So, I am not going to say much more. These ranges here, obviously the median value is in these colored bars with that line shown as the median, and 75th and 25th percentiles are shown. These are called box and whisker diagrams, which is a good way of showing quantities that vary in time, and you want to know the top. So, you want to know the maximum, the minimum, and 75th percentile, 25th percentile, and the middle range, and so on and so forth. Okay? Even when we do the extremes, that is how we tend to do it. Just a statistical approach that you should remember. So, now bringing it all together, we said the integrated assessment models are used. So, in a sequential approach, the RCPs are fed, the carbon evolution pathways are fed into these models, which give you an approximate radiative forcing that comes, because they do not have a detailed climate model in them. They focus much more on all the economy, health, transportation, energy, and so on. Then that radiative forcing is used in climate models which do much more detailed climate calculations, but they do not do a detailed human system. And then you get the net projections, which are then fed into the so-called impacts, adaptation, and vulnerability calculations. I think you know what impacts means. You want to look at how the food production is affected, energy production, water availability, health, etc., which we looked at for the modern climate, and we will look at again for future projections. How it will affect your adaptation, which means if you are living in a country like India and rice is a major crop, with the warming and precipitation changes, if the rice production is heavily affected, how are you going to adjust your food systems in terms of what you consume, what you import, what you export, what will grow, and so on, based on what climate will do into the future. So those are kind of the adaptation questions. Also, if rainfall distribution changes, wind distribution changes, how will you adjust your energy production? Where will people live, and so on. Vulnerability is along the similar lines. If you have a agricultural system, you know what is optimal for that agriculture in terms of crop calendar, temperature ranges, precipitation requirements, water availability, etc. Then what is the vulnerability of your crop system to the climate change in terms of everything: extreme rain, mean rain, total rain, temperature range, frost days, cold nights, warm days, etc., etc. So vulnerability calculations are very good. So you can find many examples where vulnerability calculations are made for natural disasters. For example, if a city like Bombay gets hit with floods all the time, how are different groups of people who live in Bombay are vulnerable to them, and how do they recover from the disasters? So vulnerability is a very broad term, which is very many methods of calculating vulnerability, which includes women's education, women's health, household income, per capita GDP, number of children, children's education, access to transportation, access to medical facilities, and so on and so forth. I want to mention that here because as we use these terms, you should at least be aware and then be able to look them up, or the modules will be provided where basic definitions will be offered for each terminology. So in the parallel approach, the representative concentration pathways are fed both to a climate model, which then feeds it to the integrated assessment, and then it feeds back to the how the actual emissions will change. So you do a feedback here and a feedback there and create projections and radiative forcing together, and then you feed again those things to impacts, adaptation, vulnerability, as well as mitigation analysis, and then you also feed them back to the climate model. So this is kind of the most realistic one, but this is also very expensive one. Okay. Just as an aside, the amount of energy consumed by the models that run these climate models and integrated assessment models, it's bigger than several countries' total electricity consumption. So we better be making sure that we are doing something useful, because we are consuming so much power just to run these computers to make these simulations. Okay. So coming closer to the projections, this is again from the document called Summary for Policymakers, which got chopped off, which will be provided to you. As I said, it's less than 200 pages, definitely worth going through without getting frazzled about the technical details. Just try to grasp the main concepts. We have mentioned before that when we look at the temperature variability and the CO2 forcing, or in general anthropogenic greenhouse gas forcings in terms of methane and nitrous oxide, are almost monotonic increases with different rates of increase over time. But the global temperatures always have ups and downs because of internal variability and so on, or more going into the ocean for some reason, or less coming out of the ocean, etc. Again, remembering that more than 90% of the heat is going into the ocean. So putting that again in the context of the increase in CO2 or total anthropogenic greenhouse gas emissions in gigatons CO2 per year, almost all of it comes from fossil fuel, and over time the contribution from fossil fuel has increased. As you can see here, this part is from deforestation and other land use like conversion to agriculture, urbanization, or abandoned land, etc., etc. So this never goes away. We always have to come back to say the relation between the anthropogenic forcing and radiative forcing and the response is always complicated because of how the energy gets moved and convected and so on. So looking at this figure again, here are the historical emissions. That's what guides the future emissions. So very optimistic scenario of RCP 2.6 will give you a range of temperature that is now considered the best way to avoid unavoidable scenarios or unmanageable scenarios. RCP 4.5 is upper end is higher and so is the lower end. We are already at 1 degree centigrade warming, so this is talking about bringing down the total warming. And these thinner lines here again are the number of scenarios that were computed by various models. So 172 scenarios here, 148. So it just depends on how many models are able to do it, how many models have all the components needed to do it, or the computing power to do it, and so on and so forth. So going from 2014 estimate here, you can see that you have a whole range of scenarios. This is because Mother Nature, we don't know exactly where she will go, because she will hopefully choose one of these. So the best thing you can hope for from the model is that you create a range of scenario which covers the gamut of possible solutions that will evolve in nature, so that you can plan for whole host of scenarios in the future. So it's never one projection, it's a range of projection. It's often also referred to as what if scenarios. What if we do this? What if we don't do this? And so on. So the what if scenarios, also called as storylines, and so on and so forth. Okay, something to keep in mind. Putting that together now to more systematic ways of looking at the projections. Here is again the range of warming. This is showing the relative to 1986 to 2005, different number of scenarios for historical reconstruction versus future projections. And you can see this is, I think, showing just 8.5 and 2.6. So that's the range there. And this is the global average surface temperature change. And this is the same, but now also showing the range for various scenarios within this band. This is going from essentially 2000 to 2100. So typically people can pick any decade or any year and then try to see where we will be. So when we come to India specific impacts and projections, we will see that typically 2030 is looked for over India, just because it's unrealistic to think that anybody is going to plan here. Pretty much the only organizations or entities that look at very long time scale right now are defenses, militaries, navies, and so on. So when they build ports, they want to know how much the sea level rise will be and so on. So everybody else is trying to stay closer to where things are able to be planned in terms of building bridges, infrastructure for energy, or dams and bridges, and so on and so forth. Okay. So this is the sea ice extent. Obviously you expect that if you have very low emissions, the sea ice extent will probably not be destroyed completely, and in fact these scenarios show even some recovery in the last few decades of the 21st century. And you see that the higher end of the projections expect that the northern hemisphere sea ice extent, which basically is Arctic, will disappear by 2060, 2070. Sitting now, you might think 2100 is so far away, but actually 2030, 2040, 2050, they are not that far away if you are in your 20s, 30s, or if you think about when your children and grandchildren will be growing up, right? They will see many, many changes, and Arctic changes are already being seen. So that is kind of a litmus test of what is happening and what will happen. So when the Arctic ice will disappear will provide a very stark contrast to what is happening with global warming and what the models are saying and how reliable they are and so on and so forth. Global sea level rise, again the range of a meter, and there are many estimates that this may be much higher than that. But again, to remember one thing, everything is got spatial patterns, as we will see. Sea level will not rise everywhere. Temperatures will not rise everywhere, even though temperatures will rise in almost all places, whereas the dynamics will move the sea level slightly differently than temperature. So another thing to remember, again, as I said before, is that as sea level is rising and cyclones are getting stronger, hurricanes are getting stronger, storm surge and inundation is going to be an issue. So if Bangladesh is sitting there within 1 meter of sea level and the cyclones increase in the Bay of Bengal, that is going to create enormous problems in terms of sea level rise, but also storm surge and inundation. And I will come and mention a little bit again, if Bangladesh begins to have more and more issues, where will those people go? Whose problem will it be if millions of people from Bangladesh want to get out because they just cannot live there anymore? So those are kind of national security issues which are included in the integrated assessment models, but in countries like India also have to worry, because if all your neighbors are vulnerable to climate change, that pretty much becomes your vulnerability as well. Something to remember, right? So surface ocean acidification, or the pH of the ocean, the lower ones kind of keep it pretty much where it is with a little bit of acidification. These are the number of scenarios models run again. But the higher emissions are going to create substantial acidification. So for contrast, remember that this sort of value has existed in the ocean for tens of millions, if not almost 100 million years, when the last hothouse created lots of ocean acidification. So this could be very bad news for not just corals and shell forming animals, but the entire food web. And considering the number of countries that depend on fish as a source of protein, that's going to be something to worry about. How do the spatial patterns look? Here is the change in surface temperature with respect to 1986 to 2005, and the range being shown is for 2081 to 2100. So change of average surface temperature here, the range for 2.6 is somewhere in this range we mentioned before. There are some uncertainties in our favorite region of Jin seas or Greenland, Iceland, Norwegian seas, where deep water formation and Greenland ice melting, etc., are meridional overturning circulation, etc., are a issue. But even in this, you can see there is a sort of a local minima there, but there are also patterns of warming and cooling. But very clear is, in both cases, there is more warming at higher latitudes, which we called polar amplification. Because of the snow and ice albedo feedbacks, we expect that the warming is going to be higher at polar latitudes. It is there here also, but less dramatic because the Antarctic ice sheet behaves because of the ocean as well. The responses are slightly different. But it turns out that the uncertainties in the models in ice sheets are also higher, and in fact many of the models do not include the ice sheets. But the new crops of models that are being used for the next assessment have ice sheet models. So this obviously will change the equator to pole temperature gradient, which means the circulation will change. Tropics will expand, so warmer temperatures are going to higher latitudes. Vegetation changes, marine ecosystem changes, combined with acidification, ocean warming, corals damage, and species distribution changes on land and ocean, and so on. So this is the change in average precipitation for the same two contrasts of two periods. So for RCP 2.6, changes are there. You can see the ITCZ showing up in both cases, including some monsoon changes. I will come back to this because there are additional complications when we do the monsoons. But you can begin to see that for higher ranges, the deserts are beginning to expand. So, there are negative changes happening even in this case. So, the Hadley cell is going to change because you change the equator to pole temperature gradient, and the subsidence regions where the air comes down, high pressure, clear skies, no rain, they are going to expand. So, you can imagine that regions in the Middle East which have lots of oil and almost all their income is from oil, and poor countries which do not have oil now are already having large civil unrest. So, if they keep warming so much and the oil begins to come to an end, how will the problems that are happening now will grow in the next 10, 20, 30 years? What will it mean for global community as a whole? All the economies are linked because of transportation, even health issues are linked, travel, migration, etc. Some forced, some unforced, some welcome, some unwelcome, and so on. So, climate change is going to become a huge socio-economic problem as well as the problem of keeping the species alive that we need desperately, and food production, energy production, etc. Sea level change, again you can see that the range here is, there are some negatives here, but mostly all positive, even though the magnitude changes over. So, northern Indian Ocean here is showing lower range than the tropical Indian Ocean, for example. Our Jinsei region is showing a local minimum, but in the high emission cases you can see that those get very well amplified to the order of a meter or more, and as I said, many newer estimates say that these are actually underestimated. So, you have to kind of consider all these things together: warming temperatures and lower precipitation, or sometimes warm temperatures and even high precipitation can mean crop damages, because crops at some point become too saturated with temperatures. They do not, the photosynthesis has a plateau and then it begins to decline at warm temperatures. I will make one point here about the reliability of projections, and I will come back to maybe mention it again when we talk specifically about Indian monsoon change. Okay. So, this is showing, thanks to the British, Gilbert Walker in the late 1800s, early 1900s, was sent here maybe in the 1900s as a meteorological officer, but before that Blandford and others had started to put rain gauges all over India. So, India has very good rainfall data going back to almost 1860, and that data allows us to say many more things about precipitation, response to warming and so on, and to aerosols or dust and pollution than anywhere else in the world. And it also allows us to make maps like this, which is showing the rainfall peak month. So, if this color, then it is peak in July, this color it's in August. July, August is the peak monsoon season, we all know that. But there are regions where June is stronger, and of course, where there is northeast monsoon, the peak is in October. So, if you take all the models, these are various models that participate in the so-called the IPCC historical reconstructions and projections. I won't go through all of them, but many US models, Canadian model, US model, Australian model, UK model, US model, Japanese model, and so on and so forth. But what you see is that the colors don't really match very well. This one seems to match July very well, but it's putting August here, no August here, doing okay with June here, but no northeast monsoon months here. So, as we said before, doing precipitation is always a problem for models. We just have to accept that, because popcorns are difficult to model. As Richard Feynman, the famous physicist, said, when we say difficult, it's like riding a bicycle. Once we learn it, it's a piece of cake, we never forget it. So when we don't understand something, we say that is difficult. So there are many unexplained, ununderstood processes that go from molecular scale to cloud scale, which is hundreds of kilometers, and the models are getting better and better at doing it, but we are still having many issues. So as I said, I will show more later that it turned out that actually pollution was reducing the amount of sunlight that was actually reaching the surface, which means the ocean heating and the land heating were happening very differently than we expected. The models didn't do the dust and pollution so well, so they didn't do the land heating as well as they should to match the observations, which means their monsoon simulation, this is for the 20th century. So, for the observed period, not projections. So, even for the observed period, their monsoon simulations are not completely reliable, which means when we look at their projections, this is the projections for those decades that we are looking at. You can see the changes projected by different models are different. A lot of them are moving the rainfall to August, a lot of yellows, but they kind of do not agree with each other at all. So, how they do the aerosol in the future, how they include the indirect effect of aerosol, which means the impact of aerosol on clouds, raindrop sizes and so on, is always tricky. But the direct effect where the sunlight is reflected or absorbed by the aerosols is also tricky, because the aerosols produced by each model depends on what kind of vegetation model they have, how the land use is changing in each model because of the vegetation model, how the sources and sinks of dust and pollution are changing, how they are getting moved. So, complicated story. Nonetheless, we have to use them as best as we can because we have a range of solutions. This is now looking more into the spatial patterns of sea ice extent in the northern hemisphere. For lower range of emissions, obviously the loss is much lower, and maybe there is even a recovery. And as you go up in emission, all the ice can be expected to disappear as early as 2060, 2080, but this is something that is moving quite rapidly. So, we will keep on collecting more and more data in the coming years and decades. So, by the time you teach these courses a few years, you will have lots of new data. So, you can see that the range in terms of million square kilometers of sea ice is quite drastic, and remember that the albedo feedback and the ice albedo feedbacks are going to be playing into this as well, and as the deep water formation and so on also will be affected. Now, we will keep getting into things that are a bit more complicated in terms of how the damage is defined, how they are projected, and how the risk is assessed. So, we talked about vulnerability, how each country or within a country, how each state may be vulnerable to climate change. But you also have to think about what are the risks to which the vulnerability has to be considered, because then obviously the third concept is how resilient any given region is or community is, and how to increase the resilience, how to reduce vulnerability and risk, and how to increase resilience. Those are kind of the goals of using the projections and the mitigation and adaptation strategies. Okay. So, I won't go through all the details, but the so-called reasons for concerns, or RFCs, are defined as unique and threatened systems, extreme weather events, distribution of impacts, global aggregate impacts. So, distribution and global aggregate, they do matter. Large scale singular events. We will look at each of them, but just to conclude this part, we will see unique and threatened systems basically include some ecosystems and cultures. So, that is not just vegetation and fish and trees and so on, but also human beings. They are already at risk from climate change. We have very high confidence on that because many vulnerability calculations have been done. With the additional warming of 1 degrees, the number of unique and threatened systems at risk of severe consequences obviously increases, which means it will depend also on the emission pathway, the RCP. Many systems with limited adaptive capacity, particularly those associated with the Arctic Sea and coral reefs, are subjected to very high risks with additional warming of 2 degrees centigrade. So, this is where using the concept of radiative forcing and looking at the response in terms of temperature begins to give you a better handle on how the cascades can be tracked and how we can begin to define our risks, vulnerabilities and resiliences. So, it also includes marine species, ocean acidification, coastal ecosystems. Extreme weather we will discuss in a bit of detail when we come to the monsoon, but as I am talking today is August 2018. Kerala has just flooded and it is expected to flood again next week according to IMD forecast, and large parts of India are flooded. Bombay flooded this year, last year and in 2016. So, these are the extreme events, and I will talk about how extreme events over India are increasing, for example. So, climate change related risks from extreme events such as heat waves. India is having increased heat waves. Heavy precipitation and coastal flooding are already moderate, we can say that with high confidence. So, with warming, we did not get into the dynamics of why rain begins to come as heavy rain when global warming happens. It is the way the vertical circulation adjusts to warming that makes it rain heavily. That is a very complicated dynamics that we will not get into, and I do not think you as a teacher you can be expected to teach at a lower level, but if you are capable of following some of the literature, it will be provided so that you can know the basics of how with temperature humidity increases and then why precipitation does not increase as much as humidity. So, if you warm by 1 degree centigrade, humidity increases by 7% using something called the Clausius-Clapeyron relation, which is an exponential relation between humidity and temperature. The rainfall only increases by 2 to 3% because of some limitations on how much energy has to be lost to space to rain out. When it rains, remember, heat is released, that heat has to be lost. But extreme events can increase by 10, 20, 30%. So, this is a very complicated dynamics, but if you remember just these kind of simple numbers, we are doing very well. Distribution of impacts is basically risks that are unevenly distributed between groups of people and between regions. So, tropics are more vulnerable as far as we know now, for example, and risks are generally greater for disadvantaged people and communities. So, we know that regional differences are going to play a role in terms of losers and winners in global warming and how the community begins to respond, and the globally connected system makes it very difficult in terms of economies, which I will talk about a little bit more later on. So, regional crop yields and water availability and so on will also begin to increase. Aggregate impacts of global warming are going to result in terms of Earth's biodiversity, which again is related to climate change, but also it will feed back to climate change, and the global economy as a whole, which is now very well interwoven. So, if you perturb in one place, you are going to have an impact in another place. With medium confidence, we can project some of those impacts. Aggregate economic damages will accelerate with warming, but right now the quantitative estimates are not very good for warming of 3 degrees centigrade. So, that is kind of maybe a point of no return or no analog state or a switch or a threshold in the system or whatever. So, we need to be aware of. Large scale singular events with increasing warming, some of the physical and ecological systems may abruptly collapse, like Amazon forest, Arctic sea ice, Greenland ice sheets, etc., come to mind. So that would be abrupt and irreversible. So the risks associated with such tipping points are right now moderate between 0 and 1 degree C as best as we can estimate. But things like coral reefs, Arctic ecosystems, which are already kind of being pushed very hard, are probably going to be most vulnerable to such points of no return or collapses or abrupt changes. So predicting abrupt change is always very difficult, but the risks increase at a steepening rate, which means they become more and more vulnerable as we increase the warming by 1 or 2 degrees centigrade, and we're pretty sure that above 3 degrees centigrade they will become potentially large and irreversible changes. Sea level rise, obviously as ice sheets collapse, that's going to be a serious concern, and any additional warming, there is going to be near complete loss of Greenland ice sheet, but the time scale is very long, millennium or more. That would lead to about 7 meter of global change. Many places like Bangladesh or even lower Manhattan and parts of all coasts in the world are going to be highly vulnerable to that kind of change. So remembering that CO2 stays for a long time, we do have to plan for those. So we will look at some of the projections which I didn't emphasize enough here, because some of them actually go further. You can see here some of them are going beyond 2100 into 2300, whereas most policymakers are only looking at up to 2100, and many countries are also only looking at 2030 and 2050. We'll come back and continue, but I hope you are beginning to get a sense of how many additional factors we have to begin to worry about compared to the past climate changes when we begin to worry about future projections. So see you next time.